Hello, friends. Welcome to Akulmach Live, and I welcome all curious minds to another exploration of our incredible planet. Today, we are diving deep into the topic that sounds like science fiction, but it is a very real and actively researched area of Earth science. Could our own atmosphere be playing a role in guiding the Earth's magnetic poles? That's a question, very profound question. For centuries, we have understood that Earth's magnetic field has a force generated deep within its molten iron core, a vital shield protecting us from a harsh radiation of the sun. But recent discoveries and ongoing research are hinting at more complex interplay, suggesting that the very air we breathe might have a significant influence on this fundamental planetary feature. So, in the next few minutes, we will take a journey from the fiery heart of our planet to the wispy edges of our atmosphere, exploring the traditional understanding of geomagnetism and exciting new evidence suggesting a powerful connection between the air above us and the wandering, sometimes slipping magnetic poles. So, friends, buckle up because we are about to unravel a hidden influence shaping our world. To understand the potential influence of the atmosphere, we must need to grasp the basic of the Earth's magnetic field. Imagine a giant bar magnet located at the Earth's core. Although the reality is far from such dynamism, this magnetic field is generated by the movement of molten iron in the Earth's outer core, a process known as geodynamo. The heat escaping from the inner core and the Earth's rotation drive convection current in this liquid iron, creating electrical current that in turn produces the magnetic field. We know that there is a relationship between electricity and magnetism. Now, these magnetic field lines extend far out into space, forming the magnetosphere, a vast bubble that deflects most of the charged particle from the solar wind, a constant stream of particles ejected by the sun. Without this shield, life as we know it would be impossible, as the solar wind would stripe away our atmosphere. The points where these magnetic field lines converge at the Earth's surface are the magnetic poles. Crucially, these are not the same as geographical north and south poles, which are defined by the Earth's axis of rotation. In fact, the magnetic poles are constantly moving, a phenomenon known as the polar wander or polar shifts. Over longer timescale, Earth's magnetic field also undergoes dramatic reversals, where the north and the south magnetic poles effectively flip. The reason for these reversals are still not fully understood, but they are as natural part of our planet history, occurring irregularly every few 100,000 years to a few million years. The last reversal was about 780,000 years ago. So that's the traditional picture. A magnetic field generated deep within the Earth's, protecting us from the space. But what role could the relatively thin layer of our atmosphere plays in this grand geodynamic process? Let's ascend from Earth's surface and explore the different layers of our atmosphere. We have the troposphere, where we live and where weather occurs. The stratosphere, home to the ozone layer. The mesosphere and the thermosphere, where the International Space Station orbits. And finally, the exosphere, gradually fading into the vacuum of space. The key player in this story are the upper layer of the atmosphere, the ionosphere and the magnetosphere. The ionosphere, a part of the thermosphere and the exosphere, is ionized by solar radiation. This means that the atom in this region have lost or gained electrons, creating electrically charged particles. The magnetosphere, as we mentioned, is the region of space dominated by Earth's magnetic field. It is a highly dynamic environment constantly interacting with the solar wind. Now, the intriguing question is, how can this upper atmospheric layer, seemingly so far removed from the Earth's core, exert any influence on the magnetic field generation or the movement of magnetic poles? So scientists are exploring several potential mechanisms. One key area of focus is the exchange of energy and momentum between the atmosphere and the magnetosphere. The solar wind, carrying its own magnetic field, interacts with Earth's magnetosphere. This interaction can drive powerful electrical currents within the magnetosphere and ionosphere. These currents, while relatively weak compared to those in the Earth's core, can still generate their own magnetic fields and potentially influence the overall geomagnetic fields. Think of it like having a smaller magnet interacting with a larger one. The smaller magnet's presence can subtly alter the larger field shape and behavior. The idea of atmospheric influence on the magnetic field isn't just theoretical. Growing evidence from various sources is suggesting a tangible connection. One line of research focuses on the geomagnetic jerks. These are sudden, rapid changes in the Earth's magnetic field that occurs over a period of few years. While the primary cause is believed to be within the core, some studies have found correlation between these jerks and events in the atmosphere, such as in atmospheric circulation of large scale weather pattern. Another key area of investigation involves the ionosphere's electric conductivity. The degree to which ionosphere can conduct electricity is highly variable depending on the solar activity and other factors. Changes in this conductivity can affect the flow of electrons and electrical currents in the upper atmosphere and potentially influence the magnetic field lines that passes through it. Furthermore, scientists are studying the impact of atmospheric escape. Our vast timescales, atmosphere slowly leaks into space, particularly at the magnetic poles, where the magnetic field lines are open. This loss of charged particle can alter the overall electrical balance of the upper atmosphere and magnetosphere, potentially having long-term effects on the geomagnetic fields. Perhaps one of the most intriguing lines of the evidence comes from studying other planets in our own solar system. Mars, for example, once had a global magnetic field but lost most of its atmosphere over billions of years. Some scientists hypothesize that the loss of its atmosphere may have contributed to the demise of its global magnetic fields. While the mechanisms are likely different from what we have on Earth, comparing planetary evolution can provide valuable insights. It's also worth considering the role of specific atmospheric component. For instance, the evolution of Earth's oxygen-rich atmosphere is a unique feature of our planet. Some researchers have proposed a link between major oxygenation events in the Earth's history and changes in the strength or behavior of the magnetic fields. The exact mechanism for such a link are still under investigation, but one possibility is that changes in the atmospheric chemistry could affect the electrical properties of the upper atmosphere, or even influences the process within the Earth's mantle that indirectly affects the core. Other atmospheric phenomena like powerful thunderstorms can reach into the ionosphere and also being studied for their potential to generate electrical currents that could briefly interact with lower reaches of the magnetosphere. It is important to remember that this is a complex and interconnected system. The Earth's core, mantle, crust, oceans, and atmosphere are all interconnected in various ways. Disentangling the precise influence of such component on the magnetic field is significant scientific challenge. Understanding whether and how our atmosphere guides Earth's magnetic poles has significant implications. For one, it could provide us with more complete picture of the processes driving polar wander and the magnetic field reversals. Predicting these events even on geological timescale could be crucial for understanding their potential impact on technology and even life on Earth. A deeper understanding of this atmospheric influence could also enhance our ability to monitor and predict space weather. Disruptions in the magnetosphere and ionosphere driven by solar activity can interfere with satellite communication, GPS systems, and even power grids. If atmospheric conditions play a role in shaping the magnetosphere's response to solar events, then incorporating atmospheric data into space weather models could lead to more accurate forecasts. Furthermore, studying the interplay between planet atmosphere and magnetic field can provide valuable insights into the habitability of the world. As we search for life beyond Earth, understanding the conditions necessary for stable atmosphere and protective magnetic field is paramount. Future research in this area will likely involve sophisticated satellite missions to monitor both Earth's magnetic field and the upper atmosphere in unprecedented details. Ground based observatory will continue to collect crucial data, and advanced computer model will be used to simulate the complex interconnections between these different Earth systems. Scientists are also looking for geological records to find more evidence of past correlation between atmospheric changes and the magnetic field's behavior. Analyzing ancient rocks and sediments can provide a long term perspective on this intricate relationship. So, is our atmosphere guiding Earth's magnetic pole? While the definitive answer is still unfolding, the evidence strongly suggests that relationship is far more dynamic and interconnected than we once thought. The thin veil of air that surrounds our planet might be playing a subtle but significant role in the grand symphony of Earth's internal and external forces. This ongoing research highlights the interconnectedness of our planet's systems and the importance of studying Earth as a whole. The secret held within the interactions of our atmosphere and magnetic fields are still being uncovered, promising exciting discoveries in years to come. So, friends, thank you for joining me on this fascinating journey. Don't forget to like this video, subscribe for more exploration of our amazing planet, and let us know if in the comments what other scientific mysteries you'd like us to dwell into. So, friends, until next time, keep looking up and keep questioning everything. See you in the next one, friends.